Water, acid and base in one. So there's that word again, amphoteric. Water can act as an acid or a base. And even in pure water, the acid will do this a little bit with itself. So here's one water molecule and another water molecule. If this one's acting as the acid and this one's acting as the base, the acid will donate a proton to the base and we'll end up with a hydronium ion and a hydroxide ion. And you might say, why on earth would it do that? Doesn't nature like things to be level and all coming together and being the same? Well, yes, it does. And so this happens very little. It happens, but on a very, very small scale. This is called self-ionization because it ionizes with itself. This occurs only to a very, very small extent. So let's look at this. That was H2O liquid plus H2O liquid in equilibrium with H3O plus, that I guess would be considered aqueous, and hydroxide ion, aqueous. We have learned how to write equilibrium constants, right? What's the equilibrium constant expression for this reaction? We don't include liquids, right? It's H3O times hydroxide ion concentration. This guy right down here. The equilibrium expression, K, the equilibrium constant, here it's given a special name because water is so special, Kw, and it's the hydronium ion concentration times the hydroxide ion concentration. This value is 10 to the minus 14. Does this reaction favor the products or the reactants? It favors the reactants quite strongly. There's very little hydronium or hydroxide ions in pure water. Very, very tiny. So we can look at this, Kw equals these two times each other and is equal to this. Well, if the hydronium and the hydroxide came from the water, they must be equal in concentration, and so we can actually solve for that, and we find that these concentrations are equal, and they equal 10 to the minus 7th molar. So in pure water, you have 0.0000001 moles per liter of these ions. Very, very low. Not enough to conduct electricity at all. And so in pure water, those are the concentrations of the ions, and pure water is considered a neutral solution because the hydronium ion concentration is equal to the hydroxide ion concentration. So it's not it's not an acid, it's not a base, because it's kind of both at the same time. It's neutral, right? So in a neutral solution, we define neutral as being that the hydronium ion concentration is equal to the hydroxide ion concentration. All of these reactions that we've been talking about, all of these dissolving acids and stuff, it's all been in water. So you can have a neutral solution with other stuff in it. The important thing is that hydronium ion concentration is equal to hydroxide, which is equal to 10 to the minus 7.
So as long as it comes up with those numbers, they're always neutral?
It's neutral. Yep, it's neutral. And in water, the hydronium ion concentration times the hydroxide ion concentration is 10 to the minus 14. So if they are equal, it's 10 to the minus 7. They can't be equal at any other concentration because of that self-ionization of water. So what we call an acidic solution has more of the acidic ion. Okay, H3O plus is the acid, right? Because it can donate a proton. So the acid concentration is higher in an acidic solution. If the acid concentration is higher, then the base concentration has to be lower. Because it's a little bit like a rope hung over a pulley. And if I pull down on this side, the other side goes up, right? And vice versa. You can't pull both ends of the rope down at the same time. It doesn't work that way. These guys are in this relationship where you multiply them and you get the same number every time. So if one goes up, the other goes down. It's proportional. In a basic solution, the hydronium ion concentration will be less, and the hydroxide ion concentration will be greater. In any aqueous solution, this ionization constant, this equilibrium constant for the self-ionization of water is always the same. It's a constant. It's 10 to the minus 14. So if H3O plus is higher, then OH minus has to be lower so that they are equal to this at all times. So there's an interdependence. So here looking at hydronium ion concentration. 10 to the minus 7 molar is neutral. As we increase the concentration, the solution becomes more and more acidic. Here's the hydroxide ion concentration. Neutral solution, this is also 10 to the minus 7. As the hydronium ion concentration increases, the hydroxide ion concentration decreases. Let's just pick one of these. Let's just pick this one right here. So if we take the hydronium ion concentration and multiply it by the hydroxide ion concentration, what do we get? We get 10 to the minus 14. When we take numbers like this with a common base of 10 and the exponents, when we multiply them, we just add the exponents. So minus 3 and minus 11 add up to minus 14. That's one of the advantages of logarithms. Logarithms were originally used for multiplying and dividing large numbers. And you had a slide rule that allowed you to find the logarithm, and then you would just add or subtract, because they didn't understand long multiplication and division. Or they just found this a lot easier. They didn't have calculators, right? You see the relationship here? This is minus 0, and this is minus 14. Those exponents add up to minus 14. Come over here, as the hydronium ion concentration goes down, the hydroxide ion concentration goes up. Here we've got minus 9 and minus 5. Those add up to minus 14. So there's this interrelationship. One goes up, the other goes down. So we can calculate the hydronium ion concentration if we're given the hydroxide ion concentration. So what we're going to use is this idea, the hydronium ion concentration times the hydroxide ion concentration is equal to 1.0 times 10 to the minus 14. Thankfully, that equation has no fractions in it. We're given hydroxide ion concentration. We need to solve for hydronium ion concentration. Always a good idea to rearrange your equation first and then put the numbers in. So I'm going to divide both sides by the hydroxide ion concentration. So then the hydronium ion concentration equals 1.0 times 10 to the minus 14 divided by, in this instance, it's 1.5 times 10 to the minus 2. Now, those numbers are both in scientific notation, and your calculator is going to care a great deal that you enter them into it correctly, or it'll do funky things and give you the wrong answer. So remember to use that EE button or EXP button correctly. So the numerator there is 1 EE minus 14 divided by 1.5 EE minus 2. And we come up with 6.7 times 10 to the minus 13. And the unit on that will always be molarity. Did you get that number? So these other two would be done in the same way. It's going to be 10 to the minus 14th divided by whatever this concentration is. B we can do without even calculating. It's 1.0 times 10 to the minus 7. Because that's the neutral solution, right? Because these two times each other give us 10 to the minus 14. Let me just give you the answer to that last one. 8.2 E. So for the last one, the answer is 1.2 times 10 to the minus 5.